Welcome back to the channel, dear students. This side, Govind, chemistry faculty, as you know. This time we are doing the biomolecule series. Already two videos uploaded in the channel. You can go through it and check it. Any confusion, you can mail me or you can comment there. Lecture number 3. Now we are going to record, and soon it will be available on the YouTube channel. So go through it once. In the lecture number 2, we have completed the preparation of glucose and classification of hydrolysis. In that video, we have completed, right? So okay. So in the next video, we are going to discuss about the structure evidence of glucose. So be with me and see the screen. In that case, on your screen it is written structure evidence of glucose C6H12O6 by Govind sir. So okay, so according to the structure evidence for glucose. So we are going to discuss about the structure evidence of glucose. As you can see in the structure evidence of glucose, first point, very slowly we have to discuss using mole concept. Using mole concept like mass percent, like mass percent or combustion product present, we find combustion product present, we find empirical formula. Okay, we find empirical formula. In that case, C6H12O6, if you are heating this glucose, it's an organic compound, carbon dioxide and water vapor will form. So the meaning is we are able to form, we are, if we are talking about the structure, so in that case, using mole concept, what is written? Using mole concept like mass percent or combustion product present, we find empirical formula of the glucose. So that is the first point in the case of evidence. Second point, CHOH 4 time and CH2OH. That is your glucose, children. In that case, if you are heating this in the presence of HI is what? Reducing agent. Okay, HI is what? Reducing agent. It's a powerful reducing agent. Then it is converted into CH3, CH2, 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 1, 2, 3, 4, CH2, CH3. It is converted into N hexane. It is converted into N hexane. So what it proves? It proves that all carbon, all carbon in glucose molecule connect with straight chain. Connect with straight chain. So that is the conclusion of the second point. Again, I am telling you, this species is glucose. In the presence of reducing agent, it is converted into N-hexane. It proves that all carbon connect with straight chain in glucose. In glucose. Okay, children. That is the second evidence. Come to the third evidence, number 3. In that case, again CHO, CHOH 4 time, CH2OH reacting with NH2OH. If you remember that reaction in aldehyde, we have already done. CH NOH, then CHOH whole 4 and CH2OH. It's a oxime formation. It's a oxime formation. That is the reaction of carbonyl compound, chemical property of carbonyl compound. At the same time, if you are reacting this glucose molecule with HCN, then what happen? That CN will attach, okay, and CHOH whole 4 and CH2OH cyanohydrin. What is forming? It is forming cyanohydrin. Cyano means cyanide, hydrin means OH group. So, on the basis of these two reactions, what you can say? You can say that it proves that carbonyl group, carbonyl group, carbonyl group means C double bond O, this group is present in the glucose structure. Either it is CHO or CO, ketone, that we cannot decide here, but it is clear that in this, by these two reactions, because these two reactions only shown by carbonyl compound, so on that basis we can say that in the glucose structure carbonyl group is present. It may be aldehyde or ketone. In the next point we will discuss. Okay, so check the next evidence number 4. CHO, CHOH whole 4, CH2OH, again glucose, reacting with bromine water, Br2H2O. So Br2H2O is what, children? Mild oxidizing agent. Mild oxidizing agent. Okay. So if you remember, mild oxidizing agent also able to convert aldehyde into carboxylic acid. So here it is forming COH. Aldehyde will be converted into carboxylic acid. Okay, it is gluconic acid. What is the name? Gluconic acid. Gluconic acid form. What it proves? It proves that presence of aldehyde group. It proves that presence of aldehyde group. So by this reaction you can say this is your glucose, and here mild oxidizing agent you are using, then this aldehyde is converted into carboxylic acid, gluconic acid. So it proves that presence of CHO group confirmed. Aldehyde converted into carboxylic acid. So simply you can say aldose. What it is? Aldose converted into aldonic acid. Aldose converted into aldonic acid. Okay. The same time, fifth point here also we will discuss. CHO, CHOH whole twice, and CH2OH. What happened here? If you are using concentrated HNO3, what is concentrated HNO3? Strong oxidizing agent. It is a strong oxidizing agent. So all the oxygen will be removed from top to bottom, top and bottom condition, not all. COH and CHOH whole 4 and COH, glucaric acid. It is forming glucaric acid. So if you remember, strong oxidizing agent converted 1 degree alcohol. See, here it is 1 degree alcohol. Okay, strong oxidizing agent 1 degree alcohol converted into acid. And this is aldehyde. It will be also converted into carboxylic acid. So what is the conclusion of this point number 5? So conclusion is, at carbon number 1 aldehyde group is present, and last carbon 1 degree alcohol. In the last carbon we are having 1 degree alcohol. This is the conclusion of point number 5. So that's it. Next, number 6. If you are using acid anhydride, acid anhydride with pyridine, then what happened? So acid anhydride, what is acid anhydride, children? CH3, C double bond O, O, C double bond O, CH3. So this is your acid anhydride. In that case, what it is forming? All the alcohols connected with CHO, CH, O, CH3, whole 4, CH2, O, CH3, and 5 CH3 COH will form. So what it, listen, if any confusion you are getting, then listen. Anhydride, if you remember, anhydride reacting with alcohol. So what it forms? It forms ester plus acid. What it forms? Ester plus acid. So this is a kind of ester formation. And which kind of ester formation? Pentaester. It's a pentaester. Okay. So these are the 6 points for the structure evidence of glucose. So after all these 6 points, what we can conclude? So conclusion, what is the conclusion? Glucose is concluded to have five alcoholic group. How you concluded that? Because here 5 times CH3CO, CH3 is attached. Okay, that is why pentaester formation. So 5 alcoholic groups and 1 CHO group. In that case, all on different carbons, all on different carbons, as the structure is stable. Okay, if they are on the same carbons, then it will be difficulty. If OH group on same carbon, then unstable species you will get. So that is why all are on different carbon. So check it once again. What we have concluded? Glucose concluded to have 5 alcoholic group, 1 CHO group, all on different carbons as the structure is stable. OH on the same carbon, then it will be unstable. So that is all about the glucose structure evidence. In that case, what is the structure of that glucose? Check it once. See, so what happened? Now, carbon number 1, aldehyde, 2, 3, 4, 5, 6. And here H, here H, all the OH this side, all the H, same side all the H we are having. So this is the straight chain structure, but stoichiometry is not accepting this structure. So what stoichiometry is saying? In that case, come to the stoichiometry. According to stoichiometry, once again I am correcting my word, not stoichiometry, it's stereochemistry, children. Little bit confusion. Stereochemistry. On the basis of stereochemistry, Fisher gave the presentation that is called Fisher projection. That is the name of chemist. Fisher gave structure of glucose. Okay. So according to the Fisher projection, we are having CHO in the last carbon, CH2OH, carbon number 1, 2, 3, 4, 5. Here OH and here H. Each H and OH position is fixed. You cannot change. Okay. OH, H, OH and H. So this is the glucose. Okay. This is the glucose. How many chiral carbon we are having? So you can say first carbon, and this is the carbon number 2. Here OH is right side, and third here OH is left side. Remember, carbon number 2 OH right, carbon number 3 OH left, then all the OH will be right side. Okay. So in that case, how many chiral center we are having? Check it. This is also chiral center, this chiral center, this chiral center, and this. So total we are having 4 chiral carbon here. Okay. Total we are having 4 chiral carbon. So if we have n chiral carbon, if we have n chiral carbon, then stereomers are, then if we have n chiral carbon, then number of stereomers is equal to 2 की power n. So here 4 2 की power 4. So total 16 stereomers is possible for this glucose structure. 16 possible configuration exist in that case. What we can say, 16 possible configuration exist in the 16 possible configuration children. In the 16 possible configuration children, only one of them is plus D glucose. What I am saying, in the 16 stereomers, only one of them is plus D glucose. Okay, so that is the stereochemistry of glucose. So now you are able to find out the stereomers also. So one hypothetical example they have given, like CHO and CH2OH, here OH and here H. So here, and the second carbon number 2, OH is right side, then it is plus D glyceraldehyde. It's called plus D glyceraldehyde. It's a simple carbohydrate. It's a simple carbohydrate. What is the mirror image? CHO, CH2OH. So here this is the chiral carbon, this is the chiral carbon. So it is L glyceraldehyde. This is D glyceraldehyde. Okay. Although in the beginning I told you that more than 6 carbon or 6 carbon ring we are having, then we are using this DL naming. So here it's a simple carbohydrate, only for the understanding point of view they have mentioned. So that rule is correct, no need to worry at all. Okay, D and L. I hope this phenomena is clear to you, and you understand the better evidence, I hope. So all the structure we have concluded, stereochemistry also concluded, glyceraldehyde and L glyceraldehyde both have concluded, and rule I told you already, if OH is left side, then D. If OH is right side, second carbon, on the second carbon, then L. So remember this concept. In the second phase, we are going to discuss about the cyclic structure of glucose. That is the important part. So be with me. Here only we are discussing the cyclic structure of glucose. Cyclic structure of glucose is more stable, because few things later we will discuss why it is stable, because that state chain structure is not explain the few things. So that also we will discuss. So don't worry. In the case of cyclic structure of glucose, before that I am telling you one concept, hemiacetal concept. Already hemiacetal concept. In the aldehyde, we have already discussed this. This once again I am telling you. So this is your carbonyl group. Here R and here H is attached. If it is reacting with alcohol, so what happened, children? Here lone pair and here this carbon positive center. So lone pair attached with this carbon and pi electrons shifted on the oxygen. In that case, carbon, oxygen is getting negative charge, hydrogen is attached, and R is attached, and the remaining species, oxygen, hydrogen, and R dash also will be attached. What happened? This positive charge on the oxygen vanished by hydrogen electron. Hydrogen gives sacrifice. From here, H plus becomes free. It will be attached with this. So simply we are getting hemiacetal carbon, OH, one hydrogen, and here R and here OR dash. So hemiacetal means on the same carbon, if hemiacetal means on the same carbon OR and OH group is there, it's called hemiacetal. So this concept we are going to use in the cyclic structure of glucose. I hope this is easy also. In the chapter also we have completed. See, so what's going to happen in the, what is the structure? What is the structure, children? Glucose structure, tell me once. Carbon, wait, carbon, oxygen, hydrogen, then second carbon, right side OH, on the third carbon, left side OH, then fourth carbon, OH, H, OH, H, 1, 2, 3, 4, 5, and the 6, CH2OH. Okay, very patiently we have to understand this. Oxygen is having lone pair, although we are having lone pair with each oxygen atom, but why I am taking second last carbon oxygen, that you will later understand. So these lone pair attach with the oxygen, then pi electron shifted on the carbon. Wait 1 minute. Here see, so these oxygen electron attach with the carbon and oxygen electron shifted. From here H plus is free, just like hemiacetal. go back, that will be attached with this oxygen, O minus. It's a intrahemiacetal formation. What it is? It is intrahemiacetal formation. It's a intrahemiacetal formation in the same molecule. So what you are getting, children? Write it here. This is the carbon. Now this carbon is having OH, oxygen, and hydrogen is attached. Then hydrogen, remaining carbon 1 2 3 4 5 6, 6 carbon position as it is. Second last carbon we are having oxygen. That oxygen is attached to the carbon number 1, and remaining second carbon OH, third carbon OH, remaining OH, and 2 3, and here one more H, here one more H, here one more H, here one more H. So check it, children. Okay. Okay, this H is not there, sorry. CH2OH. Okay, so that is the formation. Here oxygen is placed. It's called alpha D glucose. Try to understand why alpha. What is the meaning of alpha? D is clear, it's a naming. At the carbon number 1, OH is right side. OH is right side, then it is alpha. Then it is alpha. If on the first carbon where aldehyde group is present, in that case it's called alpha. Okay, so that is the product alpha D glucose formed. It's a glucose when it's a front attack. Okay, front attack on the carbon. That attack is possible from the back side also, children, yes or no? In the case of backside attack, only in the first carbon position of OH will be changed. Check it. Carbon 1 2 3 4 5 6, 1 2 3 4 5 6, last carbon CH2OH. On the carbon number 1, position of OH is changed, remaining as it is. Here H, and here oxygen is attached. It will be beta D glucose. Why beta? Because OH is left side. OH is left side. If OH is left side, then beta. OH is right side, then alpha. Remember this point, children. Okay, so this is the alpha D glucose and beta D glucose. Here carbon number 1 is called anomeric carbon. anomeric. What it's called? Anomeric carbon. Carbon number 1 is called anomeric carbon. So this product is formed from the front attack alpha D glucose, and this is forming from the back attack. So it's just simple, go through it once. Carbon number 1 is called anomeric carbon. What is anomers and epimers? So just simple, here only I am writing. Anomers are kind of epimers. Anomers are kind of epimers. Epimers means anomers, that means these alpha D glucose and beta D glucose are the anomers of each other. Okay, why anomers? From the one carbon atom, on the same carbon atom, different species we are getting, pair of compound which forms of single carbon. So what you can write? Pair of compound. Anomers are what? Pair of compound, pair of compound from which forms which forms of single carbon. So you can see that alpha D glucose and beta D glucose differs from the carbon number 1 only. On this carbon only they are differs. That is why alpha D glucose and beta D glucose are called anomers, and carbon number 1 is called anomeric carbon. So check it once again, I am explaining the whole concept. This is the glucose, this is your glucose. Intra-hemiacetal formation, OH will be attached, oxygen electrons shifted, then this species you are getting, OH is right side, then it is alpha D glucose, and that is front attack. If attack is from back side, then OH will on the left side, it will be beta D glucose, and both species are anomers. Anomers are kind of epimers, that means a pair of compound which forms of single carbon. Okay, why we are choosing this OH only? Because from this OH we are getting a six membered carbon ring. That is why, if this or this you are taking, then six membered carbon ring is not possible, children. Okay, in that case six member carbon ring is not possible. That is why I am saying this. Okay, we are using second last OH group. So check the cyclic structure of alpha D and beta D glucose. Here only we are forming. So for alpha D glucose, okay, first cyclic structure for alpha D glucose. So that is your alpha D glucose, and oxygen is attached here. So six member ring, oxygen is placed here like this. Here this carbon. What is the trick for that? Whatever in right side, that you have to place below. At the carbon number 1, right side is OH, so OH will be below. At the carbon number 2, OH right side, then it will be right side. At the carbon number 3, here H is right side. Carbon number 4, OH is right side. Then here big group, CH2OH and one hydrogen. Okay, remaining hydrogen, that is the Haworth structure of glucose. It is called Haworth structure of glucose. Check it. It's called Haworth structure. Haworth representation. It is a Haworth representation for alpha D glucose. What trick we are following here? What trick we are following? Whatever in right side, whatever in right side, that will be placed below. Okay, carbon number 1, OH, then H, OH, here H, oh sorry, in this case here it will be OH, then OH, H, CH2OH, H. So that is the cyclic structure, children. Okay, in that case this is the cyclic structure. I hope it is clear now. Cyclic structure is clear to you. Once of glucose is clear. So now, what about carbon number 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Hydrogen is attached to. So that is the alpha D. Now what about beta D? Same thing, slight change on the carbon number 1 position. Here OH will be up, this H will be down, remaining same OH, H, OH, CH2OH, H, here OH, H and H. This is beta D. Beta D glucose. So alpha D glucose and beta D glucose is clear now. Cyclic structure we have discussed here, and this structure is completed, children. So any confusion you can message me in the chat box. I will answer, and next lecture we will discuss tomorrow. Thank you, children. Please share it, watch it and like it. Thank you. This side Govind, our beautiful channel Chemistry Guru 1993. Please give your support.